Okay, section number 4 is entitled Comparison Test. The comparison test, they should not really be memorized. I mean, I don't memorize them. If you have two sequences where, say, the ANs are smaller than the BNs, and everything is positive. This is for all n. That is, A1 is less than or equal to B1, and A2 is less than or equal to B2, etc. But everything is positive. Well, if the summation of AN diverges, and BNs are bigger than ANs, remember, if AN is smaller than BN, then BN is bigger than or equal to. If the summations of ANs go to infinity, then the summation of BN also diverges. But what if BN converges? If the summation of B sub n converges, that is, you add up all the BNs and you get a finite number like 83 or 19.7 or the number pi, the number e, or the square root of 1903. If the ANs are positive, but all smaller than the BNs, then how can the ANs add up to infinity? At 1, 3, 7, 2, 1, 4, if you add up all these numbers forever and ever, and it's 11. If I take smaller numbers but positive, I take a half, it can be equal 3, 6 and a half, 1.8 for 1, I'll add on 3/4, less than or equal to. For 4, I'll add on 4. How can this be bigger than 11? All the numbers were smaller than or equal to the numbers on top. This one be less than or equal to 11. And so, if the summation of BN converges, then the summation of AN will also converge. This needs to be clear. Like you know your name, you should know this. Not using anything advanced at all. Basic logic. Okay, so those rules should be crystal clear. And those are two of them. Now, suppose we have the same thing again, except that we're just told that they're both positive. We're told that AN and BN are both positive series. Positive terms. AN and BN, they only have positive terms. Only I could erase this. Okay. Suppose that AN is bigger than or equal to 0. Actually, I think it has to be bigger than. Suppose that ANs are all positive and B sub n's are all positive. If this is true, and I guess you would say the limit as n goes to infinity of A sub n over B sub n is equal to L. Okay, is equal to L. And L is finite and positive. L is greater than 0, but finite. That is, it's not infinity. If that's true, then it must be the case that the summation of A sub n and the summation of B sub n both converge or diverge. Now, why is that obvious? if AN over BN is say equal to L, at some point that's true. They're really, really close to L. That means that AN is L times BN. AN is just L times BN. If AN converges, if at some point AN is really, really close to L times BN, and the ANs converge, well then the BNs are going to converge, because L times BN converge. If L times BN converges, divide by L and BN will converge. If AN diverges, that is, adds up to infinity, and BN, if L times BN is AN, well then L times infinity is also infinity. That is, if BN diverges, I should have said that. If BN diverges, well then L times BN will diverge. If BN converges, I think I said this all sloppy. If BN converges, then L times BN, also known as AN, it will also converge. When n is super duper large, the n tails, A sub n is really, really close to B sub n. It's really close to L times Bn. And if Bn converges, An converges. If Bn diverges, A sub n will diverge. Okay, so these are two rules that, I remember this, and I've never taught Calc 3 as a college instructor, and I took Calc 3 in 1988. Oh my, I took it, it has to be 98, no, 88. I took it 20 years ago, and I still see that. Okay. So now, you can use, they call it the direct comparison test. The first two that I gave, the first two are called direct comparison tests because we are directly comparing these two. Okay, so use a direct comparison test to decide if this converges or not. Okay. Well, I would compare this to 1 over n squared, the summation of that. Now that's clearly a p-series. And we know that it converges if p is bigger than 1, and it diverges if p is in between 0 and 1. So this converges. And what happened is that these terms are all smaller. I'm dividing the 1. We both have 1 on top, and here I'm dividing by 1 more than over here. Each of these are smaller than each of those. Since 1 over n squared plus 1 is less than 1 over n squared, and the summation of 1 over n squared converges, not if, it follows from the direct comparison test that the summation of 1 over n squared plus 1 is less than this sum is less than or equal to 1 over n squared, which converges. That is, the summation of 1 over n squared plus 1 converges. This term by term, is smaller than a known convergent series. We know that this converges. It's a p-series where p is bigger than 1. P is 2. These are smaller. It also converges. So sometimes you have to be really clever. Maybe not in this particular problem that we just done. Sometimes you have to be a bit clever what to compare things to. For example, if you have the summation of n equals 1 to infinity of e to the negative n. Okay, e to the negative n. And this is the same as the summation as n goes from 1 to infinity of 1 over e to the n, which is the same as the summation of 1 over e to the all to the n. Okay. Now, we know this converges because the summation of r to the n converges if r is between negative 1 and 1. Of course, you need to start at 0 to go to infinity. But you know what? Wouldn't this be bigger than the summation as n goes from 1 to infinity? Didn't we leave out one of the terms? Didn't we leave out r to the 0, which is 1? I mean, I can make the statement that this is 1 plus that. If this diverges, well then this diverges. If this converges, then that converges. Okay. But we are asked, so we know it converges. Now, e is approximately 1 over 2.718. Well, I want this to be less than something that I know converges. I want to know that it's less than something that I know converges. I mean, this is silliness. If I want this to be bigger, I'll put a half. Okay, I know that a half converges. I could have said 1 over 2.1. I could have said 1 over 2.7. Okay. I know that the right one is a geometric series where r is equal to a half, which is in between negative 1 and 1. So this converges. And since this is term by term, 1 over e is less than 1 over 2, 1 over 2 to the n is less than 1/2 to the n, it too converges. They both converge. This one converges since r is a half, between negative 1 and 1. I knew this converged also because 1 over e is between negative 1 and positive 1. But they asked me to use the direct comparison test. Now, okay, here's one where you might have to be a bit clever. 1 to infinity, 1 over 4 to the n plus 1. Now this is like 1 over n, but 1 over n diverges. This here is, we know that 1 over 4 to the n plus 1 is bigger than 1 over 4 to the n. Plus 4. We know that's true. Okay. We know that this is bigger than the summation of 1 over 4 to the n plus 4. Greater than or equal to, what is greater than? But this is equal to the summation of 1/4 times 1 over n plus 1. And I can factor out the quarter. Excuse me. Now, okay. So this goes from n equals 1 to infinity. If I make a substitution change, let's see if this is going to work. If I let u be n plus 1, okay, now this says n minus 1 is 0. So if I take away 2 from both sides, we have u minus 2 is n minus 1, which goes to 0. That means if u is equal to n plus 1, well, yeah, add 2 to both sides. Then u must be going to 2. If n starts at 1, then u starts at 2. So this is equal to 1/4 the summation n minus 1 becomes u equals 2. U goes from 2 to infinity, and we have 1 over u. Now, I know that diverges. Okay? I made a substitution change, and now that diverges. If this diverges, then 1/4 of it diverges. This diverges. And this is bigger than that. So it too diverges. Okay, I had trouble with the 1 over n plus 1. I wanted 1 over n. One more. Suppose we have the summation n goes from 0 to infinity of 4 to the n over 3 to the n minus 1. Now, 4 to the n over 3 to the n minus 1, this is bigger than 4 to the n over 3 to the n. Because I'm dividing on the left by 1 less than on the right. The tops are the same. They're both positive. Start off with 10, and you divide by 7 here, but you divide by 8 here. This is bigger. Okay. But this is 4/3 to the n. I mean, basically, I can call this a sub n, and I can call this b sub n. Since a sub n's are bigger than or equal to b sub n, and the summation of b sub n's, that is the summation of 4/3 to the n, diverges. Why does it diverge? Because r is bigger than 1. Or if you prefer, the absolute value of r is bigger than 1. Since a_n's are bigger than b_n's and the summation of b_n's diverge, we conclude the summation of a_n. That is the summation of 4 to the n over 3 to the n minus 1 diverges by the direct comparison test. Now, let's use the limit comparison test. The limit comparison test is this one on the bottom, right there. It's the one on the bottom. It's this one right here. We call it limit comparison test because we're taking the limit. If the limit is a positive finite number, then they both converge or diverge. And I think here you have to be a bit more clever as to what you're going to compare it to. This is the one where I think you need to be a bit more clever. You have the summation of n over n squared plus 1. Okay? And you want to know where if it converges or not by using the limit comparison test. Well, what you should think is n over n squared, which is 1 over n, 1 over n, compared to 1 over n. The summation of 1 over n diverges. Okay, it diverges. So what we want to do is take the limit as n goes to infinity of this divided by that, or that divided by this. It won't matter. Because if L is positive and you do it upside down, you'll get 1 over L, which is positive and finite. As it doesn't matter which one you put on the top. Suppose you have that limit. Now this limit is going to be 1. Going to be 1. Because limit as n goes to infinity. Since one or both of these are a fraction, I keep the top the same, and I change division to multiplication, and I flip over the bottom. It's n over 1. That is, I'm just taking the limit as n goes to infinity of n squared over n squared plus 1. Since the degrees of the top and the bottom are the same, I just divide the numbers in front of them. And if they're not there, they're 1. And 1 over 1 is 1. Okay? Is greater than 0 and finite. So, both of these have the same answer. They both are going to converge or diverge. Since the known one, 1 over n diverges, we conclude so the summation of n over n squared plus 1 also diverges. Okay, it also diverges. It will also diverge. Okay, let's try another one. Use the limit comparison test. So the summation of 1 over n times n squared plus 3. Suppose you have that. I would compare this to 1 over n times n squared. I would compare it to 1 over n cubed. The summation of 1 over n cubed, it's a p-series. When p is bigger than 1, we know it converges. So I use the limit comparison test. See, the thing that's going on is the bottom is n cubed plus 3n. And when you take the limits, you just look at the highest power. They're both going to be n cubed. You have 1 over, I'm going to use their distributive 1, the one where I already distributed. It's this divided by 1 over n cubed. The rule is straightforward. The rule for dividing. If the top or the bottom is a fraction, don't divide. Keep the top the same. Change division to multiplication and flip over the bottom. N cubed over 1. And what happens there is the numerator is 1 times n cubed, which is n cubed. And the bottom times 1, n cubed plus 3n times 1 is n cubed plus 3n. The coefficient powers are both the same. That's why I pick n cubed. So I divide the numbers in front and I get 1. And this is positive and finite. So they both have the same outcome. Since this converges, we conclude that the summation of 1 over n times n squared plus 3 also converges. These are the ones where you have to be a drop more clever to figure out what to compare stuff to. And suppose you have this one, the summation that then goes from 1 to infinity of 1 over the square root of n squared, n cubed plus 1. I mean, this reminds me of 1 over the square root of n cubed. You get the plus 1. But that's 1 over n to the 3/2. And the summation of 1 over n to the 3/2, since p is bigger than 1, it converges. Now I just have to show that the limit of this over that, or the limit of that over this, is positive and finite. The limit, as n goes to infinity, of 1 over n to the 3/2 divided by the square root of n cubed plus 1, well, this becomes the limit as n goes to infinity. You're going to get n cubed plus 1 divided by n to the 3/2. So now you have to think about it. N to the 3/2 is the square root of n cubed. So this becomes the limit as n goes to infinity, the square root of the top, divided by n to the 3/2, which is the square root of n cubed. Now, the square root of one thing over the square root of another thing, save a little space, you can just put one square root. You can just put one big square root. And then you have to remember your limit rules. You have this rule that says the limit of a function to a power. You could take the limit of the function and raise that answer to the power. And I don't care where x goes to. X can go to any number. That is, I can take the limit of n cubed plus 1 over n cubed, and then whatever I get, I take the square root of it. But that limit is 1, because the highest powers are the same, so you divide the numbers in front. 1 over 1 is 1, and the square root of 1 is 1. This is positive and finite. That implies, now no random guessing. Go back and read what you wrote, what you compared it to converge. So the summation of 1 over n cubed plus 1 converges. Okay, you have to be clever about what you pick to compare to. And if the top has the square root and the bottom does not, and you're having trouble figuring out the limit, put them both underneath the square root sign. Get them to both be underneath the square root sign. Does that mean to just make the square root sign longer? No. It means to say things like this. Okay. Now, we'll do one more. Suppose you have the summation of the sine of 1 over n. N goes from 1 to infinity. Now, the thing is, they're telling you to use a limit comparison test. And what you need to remember is this, and then to be a bit more mathematically mature, to think a little bit out of the box. This is equal to 1. Now, why is this equal to? Okay, it does equal 1. How can I recognize other problems similar that also equals 1? Well, of course, you have to have a sign. But what you're taking the sign of and what you're dividing by, they have to be the same. Okay, they have to be the same. And those things have to be going to 0. For example, if you have sine of 5x over 5x, these are both 0. And if you let x go to 0, then both of these are going to 0. That's 1. That's 1. X does not have to go to 0. But whatever is true down here, it better make these 0. And in this case, it had to be x goes to 0. If you have, limit. If you have the limit as x goes to 2 of sine of x minus 2 over x minus 2. You need a sign. What you're taking the sign of and what you're dividing by, they have to be the same. And they are. And when x goes to that number, these have to be 0. And they do. That's enough for me. That's 1. Now, if you have the sign of 1 over n, you need to divide this and the bottom have to be the same. Okay. Now, this is going to be 1 under one condition. Since you have sine, and since both of these are the same, you satisfy 2 of the 3 criteria, so you get 1. The third one is whatever I put here better make these go to 0. If I let n go to infinity, these go to 0. This is 1. This is 1. So, I am going to compare to 1 over n, which diverges. And then, actually, I don't have to write anything else. It's all on the board. Since what remains in the bottom corner, since that limit is 1, that is the limit as n goes to infinity of this over that is 1, and 1 is positive and finite. I know that the top series and the bottom series either both converge or they both diverge. But I know that when I'm comparing the two diverge. So, the summation of sine 1 over n diverges. Okay. Now, if you just have to remember this, that is, memorize it, this is 1. Remember, instead of dividing by 1 over n, you can multiply by the reciprocal. That's also 1. Those are both 1. If you have to memorize that, fine, that's 1. I mean, at this point in my life, I remember that. Oh yeah, that's the one that equals 1. But I see why. I mean, I was able to explain it. I didn't look it up just now. I see it. Okay. We'll just do one more and that'll be it. Very similar one I'm anticipating. You have the tangent of 1 over n. Maybe it's going to be a pain. Now, this is the same as the sine of 1 over n divided by the cosine of 1 over n. Now, I'm still going to compare it to the sine of, I'm going to compare it to 1 over n. So, I'm going to take the limit as n goes to infinity of my original nth term rule. Now I'm going to divide it by 1 over n. Now you should know this by now. If you have a number like 2 and you divide it by 3, then you divide it by 4, you're really dividing by 3 times 4. After all, let's have it in front of us. If I divide this by, if I multiply this by 3 and this by 3, which is 1, I'm allowed to do that. This is 1. The 3's cancel out and I get 2, and in the bottom I get 3 times 4. This is like my 2, this is like my 3, this is like my 4. You keep dividing sign of 1 over n by things, you just multiply their products. Okay, we have that limit. Now, what's going to happen here, and I was hoping it would, is I can make this a product and things will work out nicely. I really, really wanted to get sine 1 over n divided by 1 over n by itself. Times 1 over cosine 1 over n. But limits are very, very friendly. It's the limit of this bracket times the limit of that bracket. That is, I get the limit of sine 1 over n divided by 1 over n times the limit of 1 over cosine 1 over n. And of course n goes to infinity. And cosines and sines are one of those functions where you can put the limit after. That you can interchange cosine and sine. Excuse me, cosine and limit. Limit and sine you can interchange. Okay, but in this limit I won't do that because I know that's 1 times the limit of the top is 1. The limit of the cosine of anything is the cosine of the limit of 1 over n as n goes to infinity. But that limit is 0. So you get 1 times 1 over cosine of 0. The cosine of 0 is 1. 1 times 1 over 1 is 1. So what do we know? We know that this and 1 over n, both, since this is finite and positive, that tangent 1 over n, that's series, and the series 1 over n both converge or both diverge. So 1 over n diverges. So does the tangent of 1 over n. It diverges by the limit comparison test. Okay, that concludes section number 4.